for his third lecture.
Thank you, Luigi. So from here I can you stop my webcam as usual? Okay, no, I have found it. Okay, perfect. So this is lecture number 3, and it is a lecture on reinforcement learning methods, which are no more of the tabular family. You remember up to last week, we used to memorize the values of our policy and use the values of our policy to improve the policy in a table, in an array. And this means that we were supposing we had not so many states in order to be able to use them in a computer, in a table, and so on. Now this assumption is no more true, and this is summarized by the title of the slides. We have a problem. The world is much bigger than we used to think last week. For instance, just to give you some example, backgammon, which is considered a very small problem in this respect, has 10 to the power of 20 states, while computer Go has estimated number of states 10 to the power of 170. So, and I don't know if you heard about recent success of artificial intelligence in a video game called StarCraft 2, where there are the number of estimated states are more than this huge number. Just to give you the usual term for confronting numbers, for stating when a number is big or not, I just tell you that 10 to the power of 8 is more or less the number of atoms in the universe. You probably heard about this. And I really don't know how one can estimate this number, but this is. So you can see that just the number of states in Go is far away from a number that we can possibly imagine to be able to memorize in a computer. And also just such a small number is not very small, 10 to the power of 20 is more or less not tractable with usual techniques by computers. And then there are other much bigger problems. A problem can be continuous, or there can be problems like the protein folding, which is not actually reinforcement learning, but it is also a very big problem. So we need to find methods, alternative methods, because we are facing this kind of problems. Okay. Sometimes we can also store a large table, but the algorithm will be nevertheless too slow to learn the value function of each state individually. And so we need model-free, we need to scale up model-free reinforcement learning tabular technique. Well, the key observation is this one: the fact that a table is just one of the many ways of describing a function. If you remember, when we were in primary school or in the high school, maybe they were telling us that a function was given in some way like this. If you remember, they were making us this picture, telling, okay, this is 1, this is 1, this is 2, this is 4, this is 3, this is 9 and stating that this is describing a function. Okay, now we are used to think about this function as y equal to x squared, but you agree that in particular, when the number of elements in the domain of the function is finite, then this description is perfectly legit and is, I would say, the most perfect description of a function. Okay, but now we are in the hypothesis that we can't use this table. The table is too big. In many of our tasks, almost every state encountered will never have been seen before. So if we just decide to enumerate all the states as we were doing last week, just by going through every state, waiting for the state to be visited, in all the problems I was citing in the last slide, we would never visit almost every state. This means that your function is too complex for being described by a value by value approach. And so we need to approximate the function. Okay, this is the reason why we are looking for approximation methods. And why approximation would reduce the dimension of the problem? Well, this is clear, but just to understand the terms of the problem, assume you have to describe some, let's say, a cloud of points doing something like this, and then assume on this axis you have the states of your Markov decision process, and this is the value function, the value of the states. Then finding the value function means if these are 100 points, means finding 100 values. Okay, assuming that you know the states for which you are looking for the value. But once you do just a simple linear regression in this case, you can find a line this way. Let's say this line is what can be 2x plus 2, 2x plus 1. Okay, let's say this line, something like this. Then this means that once you have this, you can say that the value of a state S is equal just to 2 times S, assuming S is a number on this line, of course. And so you don't need any more 100 values. You just need 2 values. Okay, so in general, if you are doing a parametric approximation, let's go back to the slide. In general, if you're doing a parametric approximation of this form for the value function, then you are reducing the dimension of the problem to the dimension of the space where the parameters are living. Okay. This means also that when you are updating the value of a state, you are updating the parameter instead of the table. And of course, according, you must choose the parameter space dimension much lower, much smaller than the cardinality of the state space. But this is, of course, naturally happening since the state space has such a huge number of states, as I was telling in this slide. Okay. And then the next idea now, if you have a parameterization, if you have a parameterized functional, and you want to learn these parameters, then you need to do something which is commonly known as supervised learning, okay, just as a regression with a more complex functional form for the approximation methods. And then in this respect, the simple idea that we will explore in this lecture is that the concept, the idea of reinforcement learning target that I tried to teach you last week is just transferring to the idea of being the target, becoming the label in this supervised learning approach. Okay? And as a matter of terminology, you may have heard about deep reinforcement learning, and we are entering now this week in deep reinforcement learning, meaning that the reinforcement learning is called deep when the approximators used are the so-called deep neural networks. Okay, so we are now looking at how approximation works in reinforcement learning, and so we are learning more or less deep reinforcement learning. Well, so next natural question is how to use the approximation. Well, I already told you in the last slide, but now I'm going to be more precise. Remember, for the tabular reinforcement learning, I wanted to estimate a state, let's say a state S, and let's say maybe this state value, let's say the state value is 42, then I was doing some estimate of the state with the method I prefer, let's say Monte Carlo method or temporal difference method. I find a new value that I called, if this was VK, I found a new, a new estimate, let's say 43. Then if you remember, I formed the error that was 43 minus 42. That was the target minus the obtained new estimate minus the previous value. And then the new value was just 42 plus a certain learning rate times this error. Okay. And instead of writing what I'm suggesting now, instead of writing this equation as this, we now write just S is moving towards the target U. The target U is any target you can imagine with any method you know or you can think of. Well, the idea is the following. Just use this as training data for supervised learning. You see, for instance, deep neural networks or any regression methods with a lot of parameters, they need a lot of training data. And in this sense, reinforcement learning just comes as a generator of training data. And this is why they go together so well. Then they work very well when used together. Okay, for instance here, not for instance, these are the three main kind of labels we learn to generate with reinforcement learning. If you remember, in the first lecture, when we have done what was called dynamic programming, we were moving the value of our states toward the target that was some sense a perfect target, that was the expected value done with the model, if you remember, with the transition probabilities, the expected value of the estimated one step forward value. Remember, I take the reward and I look at the estimate in the next state, and I take the sum of them with the discount factor. I say this is my new target, I think, my estimation of the new value, and so I will move the previous value of the state S toward this new target, but not only this one, but the expected value of this target according to the transition probabilities. Okay, this was a target. Well, of course, this target cannot be used from lecture 2 on because this target is not model free. This target needs a model. And the other two, instead, are the labels that we learned how to generate in the model-free lecture, in the second lecture. Remember, in the second lecture, we said, okay, we can use as a new value for the state the total return. I'm using the slide also as a quick recap of last lectures. Okay, this was the total return. That is the sum, the discounted sum of all the rewards I get starting from a certain state. I go till the end of the episode and I collect all the reward, I get the total return, and I say, okay, this is my new estimated value. And then there was this method called temporal difference that was making just one step forward. That is, I just look at the immediate reward, and then I use my previous estimate of the value of the state to form the new target. One step return. Well, both of them can be used as target, as label for training data for our approximation method. Okay, just as a formal question, can you just look at these three targets and tell me if you notice one difference? I mean, one of them is different from the other two with respect to something that will become important. So I'm asking you if you can spot this. As a mathematician, there is something formally different from two of them with respect to the other. Waiting for the answer.
The zero parameter in TD0.
Okay, this is a matter of notation.
What do you mean?
But yes, okay, but this is not the answer I was looking for. Okay, thank you for trying. Anyway, I will tell you in
Is
next
it?
slide.
Yeah, is it we compute the expectation in the first line?
Well, you say in the first there is the expectation, and the other one there isn't. Okay, this is also true, but this just is this point that the first needs a model. Okay, no, there is a third. There is another reason why one is different, and there is a reason that will be significant in next slides. Would you like to give another try?
I'm not a mathematician, but the second one looks very different from the other one, also because the total return is calculated in a, let's say, in a deterministic way by exploring all the states, maybe.
What do you mean by deterministic?
I mean, I have to go till the end to find the total return of a state. So it's not a matter of calculating an expected value or just a one-step return.
Okay, so I would say that what you are describing is the fact that the Monte Carlo method is an offline method. This fact that you need to go till the end is described by this technical word. Monte Carlo is offline, while temporal difference is online.
Yeah, exactly.
This means exactly this. Thank you for trying, but this is also not the correct answer. Okay, but at least you are trying. We will see the answer in a few slides, don't worry. So now we are saying that we are using reinforcement learning to generate training data, okay? Well, let's think about it with respect to classical regression problems, okay? You have new problems arising in this respect if you want to use reinforcement learning targets as training data. For instance, usually, not always, but usually in classical regression, the problem you're facing is stationary, meaning that you are trying to learn a function that you assume is there, is the function solving your problem, and it is not changing, okay? It's a relation between quantities that you are assuming exist and so on. So the problem is stationary. While in reinforcement learning methods, in the reinforcement learning, for instance, prediction step, if you use bootstrapping methods, that is, if you use temporal difference, let's cross out the dynamic programming because it is not model-based and we are not interested in this. But then the value function is changing because every time you are learning the estimated value function, not really the value function. While, of course, if you're doing Monte Carlo methods, you are learning the value function of the policy, which is fixed. But this is also only in the prediction step, because in the improvement step, also the policy is improving. So also Monte Carlo methods that are looking for the return, total return given by a certain policy, when after one episode that policy is improved, is changed, the total return you're trying to predict will be changed. And so also the target function will change. You see, because we are approximating a policy which is changing. So what we are approximating is changing. This means that the stationarity assumption that we have in classical regression, making classical regression working, is failing. Moreover, usually in classical regression, you have the data you are working on are distributed in the same way, are independent. And in reinforcement learning, you have seen that we are learning usually online or offline, but in both cases, we are learning following trajectories. And think about it. If I am in a state and I evaluate the value of that state with any method, and after that, I choose as next training data the value of the state and the value of the state that comes just right after the state I was starting from, the two quantities are highly correlated, right? Because they are in the same trajectory. And so also the idea of independent and identically distributed training data is failing. So when we are using methods that relies on EED data, we have to be careful. Okay, so several new problems arising. As usual, if you have questions, stop me.
Sorry,
May I ask, so it's probably a kind of trivial question. It goes back maybe to one slide or so before. So here the function that we are trying to approximate is the value function, right? Is the v.
May I just partially answer this? The value function we are trying to approximate in the prediction step will be the value function of the policy. In the improvement step, we will be trying to approximate the optimal value function.
Okay.
Anyways, yes, it is a value function of a certain policy.
And so if we think of a linear regression case or whatever other method, then essentially we are trying to build a model for this function, right? You said the training data for the model for V, for example, V of the policy of V star, what are exactly the training data?
Training data for regression, I mean, the training when you
for
supervised learning, I mean, when you do regression with supervised learning, right?
Sure.
You have a training set.
Absolutely, yes. So even in this case, you said we are having some training data, which I think you said they are given by the reinforcement learning algorithm itself, or maybe I'm confusing myself. So are we here also in a sort of supervised learning, even now, are we in a supervised learning situation, and what are the training data?
Okay, so this is exactly the point. If you are asking because you are thinking it can't be so simple. I mean, I know how to do supervised learning. I know how to do regression, at least linear regression. Maybe you also know how to do regression with neural networks, deep neural networks. Can't be so simple. Can be deep reinforcement learning just another instance of this kind of problem. It is exactly this. The idea is very, very, very simple in a way that I'm going to explain more clearly in the next slides. Reinforcement learning in this setting is just, I underline just, is only a generator of training data, a generator of training samples. Okay, I don't know if this answers your question.
So yes, so it does in part. So I'm really trying to understand. So we are trying to build a model, let's say, for V pi, for example. So if I think of linear regression or any other kind of regression
tell me what you mean by we are trying to build a model, because you know this word model is very.
So if I think of a linear regression case, right, we have a function, we are trying to approximate it as a linear combination of the input. So we are building a statistical model for that relationship between outputs and inputs.
Okay, so for linear regression, you would need to build the features.
Yes, exactly, the features, okay. Exactly, yes.
Instead, if you're using a deep neural network, you just need to choose the neural network.
Absolutely, exactly. For the neural network, it would be all the
okay. So reinforcement learning is not helping you in building the model. You will still have to choose the model. That will usually be a deep neural network, okay? Reinforcement learning is giving you the training set for training this model.
Okay. So probably, yeah, it is definitely clearer than before. Probably by going ahead, it will be.
Yes. In which way reinforcement learning is generating this training set is the argument of this.
Oh, okay. So this is not obvious. Okay.
Well, sort of.
Or at least, I mean, okay, perfect. Thanks.
Okay, so let's enter into the details. And as usual, we are focusing for now for a fixed policy, okay? You should have now the sensibility of associating the word prediction to the fact that we have a policy, the policy is fixed, we are not improving the policy, we are just trying to find, or better approximate, the value function of this policy, okay? Which is usually denoted this way. Usually the value function of the policy was the value function of the policy for every state, but now this value function of the policy for every state is no more possible to be done. So we will have a value function of the policy, but parameterized by a vector v. Okay. And consequently, we will denote this approximation no more in this way, but with the notation which is stating the fact that this is an approximation. So something like this. We are estimating the value function in this way. Okay, so this is our approximation, the term I was describing to you right now, okay? In whatever way you have chosen this parametric approximation. So just to repeat, this can be a linear regression model. This is the model in the language you were saying now. Oh, what's happening? Okay. This is the model. Okay. Assume you have chosen the model, meaning that you have chosen the functional form of your approximator and the dimension of the parameter space. And let's call D this dimension of the parameters. Now, before learning how to build the training data with reinforcement learning, first of all, we need to decide a way to evaluate the quality of our prediction. In the statistical language, can be we need to choose the loss function that we want to minimize. Okay. Now, how we decide? The question is, how do we measure the quality of prediction? How do we decide what is the objective function to be minimized in order to say that our model is learning, that our model is training, and so on? First, we should ask the previous question. Why in the tabular case there wasn't this question? In the tabular case, if you remember, we never asked how to tell if a value function is better than the other one. Why? Because we were not approximating the value function. We were just going to the exact value function. And when we reach that value function, that is the maximum quality, okay? And if you have one single value that is not good for that value function, I'm referring to the tabular case, then you just change that value and no problem. You are improving your value function because that value was wrong and now is better than before. And you can change, the key point is that in the tabular case, you can change one single value while every other value is unchanged, okay? This is absolutely not possible with approximation. When you are changing one single value of the parameters, let's say you have 100 parameters and you are changing one single of these parameters, the second one, then the value of several states is changing. Of course, because the parameters are 100, but the states are 1 million. So one single update or one single parameter will change the value of several states. Okay, in this sense, the value function that we are finding is just a compromise. And in this, with this compromise, we have also to choose a compromise on which states we should consider more important than others. Okay, this is just to arrive to the fact, to this sentence, that we need to decide which are the states we care most. What do I mean with this? I mean that maybe you can think that in classical regression, I mean, what would be in classical regression the loss function to minimize? Let's say it this way. Assume, yes, we can do this. Let's say that your training set for your data is given by the states, and the label is the true value of this state. Okay, let's forget with approximation now. if you want to train an approximator on this training set, which kind of loss function would you use? In classical regression, I mean.
The sum of the squares of the differences between the real value, so the v pi and our approximation, our guess for what v pi should be, in essence.
Perfect. So I would do, I think, this one, right? As w minus v pi of us square. Perfect. And do you agree that in doing this, you are implicitly assuming that every state is equal? Is this correct? Every state has the same importance, I mean.
Sure, yeah.
Exactly. But now you can't do the sum. So we need, in some sense, to accept the fact that we need to consider less other states than others, I mean. So what I want to say is that we need to decide a state probability distribution, an importance for states, for probability distribution, measuring in some sense the importance of the states. This is actually this is also for another reason. If you think about this, when you are in a Markov decision process or in a problem which has a certain dynamics behind, and you follow states according to this dynamic, it is very natural that maybe there are states which are possible but very unlikely. Okay, so in some sense, the environment, the problem, the MDP is already giving you a way to decide which states are more important or are less important. And in fact, the distribution that you use to weight the sum, you see the sum is exactly the same as the loss you were suggesting, but with the difference that states are weighted by a probability distribution on the states. This probability distribution that we have to decide, in some sense, a priori, is a datum we have to put in the problem. This probability distribution, when we are doing on-policy training, is called on-policy distribution. Now, in a natural choice for this, as I was saying, is what is called the steady state distribution for a Markov decision process. Remember, we have a fixed policy, so you can forget the action part. The actions are just becoming part of the environment because you are choosing them always in the same way. And so you have what is called the Markov reward process, and you don't use the reward actually because you are not using it to improve the policy for the moment. And then you can think about the the steady state distribution that is in some sense measuring the time you are visiting the state. Okay, when you're following trajectories. I'm not sure I was clear here, so if you have questions. So the idea is that I need a loss function for my model. The original idea for the loss function would be this. This means we are using a Euclidean metric in the value function space to state whether our approximation is far or close to the true value function. But then we realize that maybe we should decide certain states to be more important than others. And so we use this weight distribution that for the moment you can think just as a datum you need to put on the problem. But I told you there is a way to choose it in a natural way.
One question about this.
Yes.
Can I? So basically, to have a practically feasible summation, this on policy distribution should contain a lot of zero, let me say, so that we can sum over a not so big number of states.
Well, after now you see I wrote this sum, this huge sum that we cannot really compute over all the states. I wrote it on purpose as an expected value, because next step will be to sample this expected value by single elements, by single instances of this value. So I will just take single summands of this big sum.
Okay.
And I will use stochastic gradient descent if you're wondering what we are doing, but in the next slides.
Okay.
But yes, the idea is that I'm looking for a way to approximate this sum, which is a huge sum that I can't anymore assume that I can do. Okay.
Okay.
Anymore to sweep through every state. I don't need to have several zeros in this distribution. I just need to have states with a very small probability of being visited. Okay.
I'm sorry, can I do a question?
Yes.
So if I get it right, you sample from the environment some states, and you compute this state probability distribution. That is basically the frequency in which you be in a state.
Careful. I'm not computing the distribution. I'm interested in the expected value of this quantity. So I'm just sampling states from the natural distribution of the environment. And this means that automatically, in some sense, the expected value I'm measuring, I mean the empirical mean, will be, in some sense, the expected value I'm looking for. So I'm not previously computing the distribution and then doing this expected value this way, if this is what you were suggesting.
Okay, thank you. Okay.
But anyway, there are other slides on this, okay? I want just to point out a single detail now, that this is just a choice. I mean, we are now deciding to train our model to declare that the best value for parameters are the values that are minimizing this expected value of the states, okay? But remember that what I want to do with the value function is to use it to build a policy, okay? And the fact that the better policy, the best policy we can find is corresponding to the value function that we approximate by minimizing this loss function is not at all trivial. Actually, there is no theoretical ground for this. So this is an open research question, meaning which kind of value of loss function we should use to train our model in order to solve the reinforcement learning problem, and not in order to find the value function which is minimizing this loss. I mean, okay. This is just an open problem. This is, in some sense, connected with this remark. Assume that the approximation method is continuous, as usual it is. is continuous for some topology on the state space, okay, then this means that this approximation will transform states which are close to each other in estimated values which are close to each other. But in order for this to work, you need that the topology of the state space is compatible in some sense with the true value function of the states. That means that states which are close in that topology must really have true values which are close. Okay, so what I'm saying essentially is that we don't know if this objective is the correct one, but there are no alternatives as of today. So we use this one, okay? And from now on, we are assuming that we want to minimize this objective. This was just a digression in some sense. Okay, now I'm trying to become more precise. So maybe I can open something to write. Okay, so first, if we can observe every state, this is a recap of what I'm saying, and now I try to be precise. If assume I can compute this huge sum, then we can find an argmin over the parameters of this sum. Okay, and this probably would be done with gradient descent. Okay, but this is not possible. Okay, this is not possible, and what I was saying is that it is also wrong. Why? It is not possible, of course, because I can't do this, and it is wrong because it is stating that all states are equal, but depending on the problem, some states are more equal than others in some sense, okay? Thus, we decide a priori a distribution that on policy distribution that I was talking about before, a distribution that is weighting the states in order of importance. And this distribution is usually the on policy distribution, that is the frequencies of visiting the states in continuing processes of the normalized time spent in every state in episodic Markov decision process. And then we decide, in some sense, a priori, that we are interested in finding the optima of this expectation that is still a huge sum. And this is what I was writing before, the same here. And this is just the expected value of the states sampled from this distribution of this, which is still something that we can't really compute, because notice that there is something that we don't know. So also this big gradient, let's say this is VA, so we need to compute the gradient of this big function. I can't, so I need to estimate this gradient. Now, how can I estimate a gradient of an expected value? This is classical. I just sample this. So I just take single instances of this. I take this with S sampled from me. And now another step, which is the reinforcement learning part. The reinforcement learning part is the fact that I don't know this, right? We don't know this label. So we need to estimate also this label. How can you estimate this label? Remember the I was talking about target just last week. I was telling you, please remember this notation, this terminology. Think to the target as an estimate of the value. In fact, you are moving your previous value toward this new value. So this is an estimate with some variance, with bias and so on. But this is an estimate of the value. So replace this with a target. Any target you like. Okay. You understand that this part is crucial. For instance, just to be clear, if this distribution is just distributed, concentrated on two single states in equal part and 0 on every other state, then this argmin we are looking for, that we are estimating in this way, would be just the average of the two values, right? It would be just 0.5 times the value of S1 minus its estimate plus 0.5 the value of S2 minus its estimate. Okay, so this is crucial. What distribution you are using is crucial in making, in deciding what you're actually minimizing once you sample these values from this distribution. Okay. So let's go back to the slide. And this takes us to this cost function, the first block, where I write that the cost function for one single training element should be, the training element should be this one, okay? But since we don't have the real, the true value of the state, our training element is this one. The single cost function is this one, should be this, but we can't use this because we don't have the true value. So we use this surrogate cost function instead. And then the error needed for the gradient descent is just the gradient of this cost function. Okay, and we put also 1/2, of course, for removing the ×2 here when doing derivatives. And since we are doing gradient descent, there is also a minus. Okay, so the error, the quantity that we need to add to the previous estimate in the gradient descent algorithm is this one. You can notice in this expression that there is 2 times u minus the estimate of the state. U, remember, is the target, okay? Can be the return for the state S, or the one step forward return from the state S, or whatever other target you can imagine. For instance, the n step return, or other methods that we haven't really described. Okay, so and then of course there is the gradient of the approximator. This is the important part when choosing the approximation methods, because must be an approximation method that is differentiable, for instance, because you need to use the gradient descent method, and maybe for which you are able to compute in a very efficient way its gradient. Just to understand, for a model is not uncommon to have 100 millions of parameters. Okay, just if you're thinking to 100 parameters, forget it. We are talking about models with 1 million, 10 million, 100 million parameters. And so doing a gradient of a model with 100 million parameters, essentially you can just use backpropagation and techniques of deep neural networks. But this is another story. Okay. Anyway, remember that there is this derivative involved. Anyway, once you have the error, you can just improve the gradient, making the gradient descent algorithm stochastic, because you just take one single state, you take the previous estimate, and you update this estimate with the error. You add the error, okay? That is this part. And this gives you the new estimate. So if this is not clear, I mean, what I'm saying here is just a quick explanation of what is stochastic gradient descent. I'm saying this, that if this error was done on the total of the loss function, that is that huge sum, that is the sum over every state, then you would be doing gradient descent. This algorithm would be called gradient descent, okay? In the moment that you take the state, just one state, and you update the gradient for just a partial direction, this is a partial gradient of the whole sum, then you are doing stochastic gradient descent, because of course these states, you are taking them in a stochastic way. And I would say it's very natural. I mean, it's a theorem actually, but you can imagine that if these examples appears with distribution me, if these examples are taken with respect to the distribution for which you are computing the expected value as a loss, then this stochastic update rule, I'm saying, of course, I mean, just natural, will just give you a minimum of this function, just like the gradient descent will give you a minimum of the function. Okay, this statement is not precise because we need the usual stochastic approximation theory assumption, but this is just to tell you that it works. Okay, questions? Okay. So you see the label we are using here. I'm already answering the previous question. How do we build the labels, the training data? The training data are given by the pair state and the target. And for this reason, the training data sorry, I would like to remove this. Do you know if I can remove this part which is covering the title of the slide?
We don't see it.
Ah, you don't, okay, perfect.
Okay.
Okay, so reinforcement learning is a generator of training samples, and these are the three targets that we can use. This one just forget and look only at, because it is not model free, and look just at this and this. If you follow it last week, then you can recognize this as a Monte Carlo target and this as the temporal difference target. So for the moment, nothing new, okay? I'm just rewriting previous slide where I'm writing explicitly the target we are using in these two families. Okay. And remember, will be important later, that this estimate is unbiased, and this estimate is biased. This has high variance, so one good and one bad, and this has low variance. Okay, now look at this slide, and now it's time to answer the previous question. There is a mistake in this slide in some sense, which is related to the question I was asking in the beginning. That is, the question was, can you spot a difference between the three targets? And now let's say between these two targets. Can you spot a remarkable difference between this target and this target that makes the gradient descent algorithm working here, SGD works, and here SGD, stochastic gradient descent, doesn't really work. So now my question is
an estimate of V
Say it
there.
again?
So we already need an estimate of V in order to compute the target there in the TD.
Okay. And well, okay, we have the estimate at time t, and we use it to estimate at times t plus 1. This, I mean, also, oh, you mean because it is in the target? Okay, and why this is a problem? Yes, the answer is correct, but can you tell me more precisely why this is a problem? I can go back with the slides, and I can suggest to you that these two boxes are related to this question. You say that the right thing. The target in the temporal difference case depends on the parameter. And then in this case, the second box is wrong. Why?
Oh, the derivative.
The derivative.
The derivative with respect to W is also like it's inside U as well.
Exactly, exactly.
Okay.
If U depends on W, then derivative of J is equal to something different. Is different from here. I mean, there is another factor. Okay, you have to multiply here for the derivative of the target, the derivative of the target with respect to W. Okay, so this is not the complete gradient. This is in some sense a semi-gradient. And this takes us to the next slide. That is exactly the fact that, forget this, the fact that this target depends on W, and thus the update rule uses only part of the gradient, which we have seen. And for this reason, this kind of algorithm, I mean, updating the parameter value with that update rule, which we can still do. I mean, nothing prohibits us of doing this, right? We can do this. Just this is not updating in the direction of the gradient, but this is an algorithm. Now we have to ask, does it work? at least it gets closer to the correct value function. Well, when I want to point out that I'm using temporal difference in this setting with the partial gradient in this way, I can state that I'm using semi-gradient temporal difference method. Okay, and in general, you can imagine that every bootstrapping method is a semi-gradient method. Okay, now just as a curiosity, one could complete the gradient, right? One could try to build an algorithm out of the full gradient. I mean, inserting in the update rule here also this part. And consequently putting some more here. If you do this, you obtain an algorithm which is called residual Bellman gradient method. And it is a method, it is a legit method, it works, but it is, I would say, much worse than the semi-gradient temporal difference method. And for this, there is a paper discussing the difference between the two algorithms, giving you some motivation and some evidence that the residual gradient Bellman method works, is worse than the semi-gradient method in a paper that I put in the share folder. Okay. So just you're just starting looking at the fact that now everything is possible. I mean, you can try everything you think about. Also things that has not a theoretical ground in some theory telling you that it works. I mean, the semi-gradient temporal difference method, updating the gradient in this way with the partial gradient is not an instance of stochastic gradient descent. So why you should use it? Okay, you use it because in experiments, in empirical way, you see it works, and then you find also some theoretical evidence of how it works and why it works. Okay, so just to let you relax a moment, just look at the code, how simple it is. These are just the initialization part. As usual, you have the input, that is the policy you want to evaluate. You have the model, okay, we call this the model. And we have some parameters for the algorithm, usually called hyperparameters, because the parameters are the one from the parameter space. And you start for the gradient descent, is an iterative method. You start from an initial value for weights, and maybe you can just assume they are all 0. And then you generate an episode. This means this line should gives you the information, if you are starting getting all the idea, that this is the pseudocode for the Monte Carlo method, because I'm doing a whole episode. And then for each step of the episode, I loop, and what I do, just for each step, I update the previous estimate. If we are in the initial value, this was 0. I put in this, in a vector, memorizing the values for these parameters. You see, I always use a table to memorize these values. Of course, I'm using a computer program. I'm using a table to memorize this vector, but the table is not memorizing the values for every single state. It's memorizing the values for every single value, for every single parameter. Okay, if I was saying this was 0, now will be 0 plus the difference between the newly evaluated target minus the original estimated value for this state, for this visited state, according to the original value of the parameters, times the gradient computed in the original value of the parameters. Okay, so I'm moving my weights, I'm moving my parameters in the direction where they minimize the loss function that I'm considering. The loss function is the square of the difference between these two quantities, and the fact that I'm taking steps following the environment, that I'm following the episode, means that I'm visiting more often states which are tautologically more important. Why I'm saying tautologically? Because I defined the importance of the states exactly in this way. I consider more important for this problem the states that, when doing episodes, will be visited more often. You see the naturality of what I'm saying. Okay, you see here in the algorithm, there is no evidence of the on-policy distribution, the theoretical one we were referring to in the beginning of this lecture. It's just automatically minimized by the fact that I'm choosing states this way. Okay, I'm not repeating everything for the next code, just pointing out the only thing that is changing, that is the update rule. In this update rule, the target is now no more the complete return, but just the one-step return. And consequently, I'm not taking steps for all the episode. I just take one action and I observe what happens. And so this is, of course, temporal difference, semi-gradient method. Why semi-gradient and not full gradient? Because here we don't have the missing part, and we never have this missing part because this is the algorithm that we use. Okay, while you think, if you want to ask questions about this slide, just something to point out is the fact that when we are moving to control, to improvement, we are no more evaluating the state value function, but we are evaluating the quality function, the action value function. But remember that everything is the same. Instead of evaluating the value of a state, I will evaluate the value of a pair state action, and so on. Okay. So what about convergence of these methods? Well, stochastic gradient descent in general is known to converge to a local optimum when the target we are using is unbiased, meaning that the expected value of these targets equals the function you are trying to approximate. This means that in our respect that between the two methods that I'm showing you here with these pseudocodes, that is the Monte Carlo gradient method and the temporal difference semi-gradient method, the only one converging truly to what we are looking for is the Monte Carlo one, because all methods using a bootstrap that are also the semi-gradient methods for the very same reason are biased. Okay. Okay, here there is a question. And do you think that this is guaranteed to converge to a local optimum is correct, or maybe we need additional hypotheses? The answer is yes, we need additional hypotheses. Can you guess what they are? I mean, you should have the sensibility now to to guess them because we already met this kind of hypothesis. This is
The
very
learning
familiar.
parameters, like with a
Yes.
constant learning parameter, we have the usual problem of oscillating, I think, right? So it
The-
should go to zero essentially with maybe
Yes, exactly.
conditions.
Alpha must be, let's say, alpha t, and must go to 0 fast, but not too fast. And this is usually expressed by the fact that the sequence of learning rates must be in L2, but not in L1. The squares must be integral, summable, because this is a discrete sequence, and but their absolute value must diverge. Okay, these are I don't remember if I told you, these are called Robbins-Monroe hypotheses. Robbins-Monroe are the guys starting this stochastic approximation theory. And more or less, whenever you're asking for a stochastic algorithm to converge, you have similar conditions somewhere. These are the minimal requirement for an algorithm to converge. Okay, now we are saying that bootstrapping methods doesn't converge. Bootstrapping methods do not converge in general, right? So why should we use this kind of methods? Well, remember that Bootstrap improves the variance. Bootstrap methods has a very, very lower variance than Monte Carlo methods. This means that when you are learning, the learning is much, much faster. Moreover, Monte Carlo methods, I said it several times, just worth to be pointed out again and again, that you can use it only when the decision problem, the MDP, is episodic, because you need to finish the episode. Okay, of course, you have several tricks to turn a continuing process into an episodic one. Maybe you can just decide to stop every trajectory after, I don't know, 200 steps, and then you are creating artificially. But this is a new problem, and it is more or less equivalent to the first one, only if when there is a discount factor, maybe high, so that when you're going forward in the trajectory, then the reward you are getting is smaller and smaller, and so on. But in general, with bootstrapping methods, we do not need the episode to finish, and so we can do what is called online learning. And this, for this same reason, means that we can use it in continuing problem. And importantly, they actually, I told you, they do not, we do not have a theoretical ground to say that they works. Actually, they do converge in a very important case, that is in the linear case. The linear case is the one when the approximation is done by linear methods. Okay, let's say linear regression, meaning the approximator is linear. This is the only part of the theory where we have several theorems and something to ground to when we are moving to neural networks more general, which are not linear. And it is worth to be described in a little bit more of a detail. So we are now starting describing what happens when the approximation method is linear. Okay. Waiting for questions, just in case. I'm trying to keep a a slow pace for this lecture because things are a little bit more complicated than last week and are becoming more complicated now. So please feel free to stop me if you need it, if you need time to digest, and if you have questions. What does it mean, linear approximator? Remember, when you choose that the approximation is linear, this means, first of all, that the loss function that you are using is this scalar product with the weights. And this in particular means that the state is described by a certain amount of numerical features that are in the same amount as weights. Okay, so if you have 100 weights, this means, in order to make this expression meaningful, that you need to have the description of the state by means of 100 features, 100 numerical quantities. Of course, usually you do the opposite. You first decide the features that are all the quantities that you need to describe completely a state. So you decide that every state is described by a vector x of features that we can say are x1 up to xd of s. So these are d numbers. This is a vector in the parameter space. This for now is the feature space, but for what I said will be also the parameter space. And in a more noble way, you can think about the feature vector as a vector of functions. These are functions on the state space. For the non-mathematician, remember that r to the power of a set means, just by definition, the set of all the functions you have from us to r, okay? And so this is a shortcut to say function from the state space to R. So this is usually chosen as a basis, otherwise you are just wasting resources. I mean, if x1 plus x2 is equal to x3, then there is no reason to use x3 as a feature, right? Because it is just described as a linear combination of x1 plus x2. So usually this is a basis. No, it's not a basis. I mean, they are linear independent, sorry. Linear independent, just. And of course, these features, you have to think about them as the quantities that you need to describe the state. I don't know if you play chess several years ago. Actually, these are part of the features used by the Deep Blue software that beat the world chess champion in '97. If you played a little bit of chess 20 years ago, there was this fact that you were using numerical quantities. If you remember, the value of a pawn was 1, the value of a queen was 10, the value of a rook, if I well remember, was 5. That is more than the value of a knight, that was 3, and so on. And these numbers were associated to the chessboard and used in some advanced way to form a feature vector that was the vector used by Deep Blue to make his evaluation, his prediction of the value function of the board. Okay, Deep Blue used, I guess, 8,800 features for his prediction. And okay, oh yes, it is written here. what are features? Pearson problem configuration in chess. You can think of something similar in Go, but these are not used because they don't work. There are not really humanly crafted features for the Go problem. And you can take the feature as a trends in the stock market or in the cart pole problem, where you are trying to balance a pole on a cart moving in a one-dimensional way, left and right. Then you can use the angle and the angular velocity, for instance. Okay, anyway, you have a problem, you describe the states with numerical quantities, you call them features, and then you form this approximator, which is just the scalar product between the weight vector and the feature vector. Okay, in this case, you can imagine everything is much, much simpler. Why? Because the cost is just this. That means that it is quadratic. Usually here you have a complex, intricate, advanced functional expression that can be very, very nonlinear. And so the square of a nonlinear thing will not be a quadratic expression. In this case, the cost is just quadratic. And it is this one. And this means that the error, the derivative of the cost, is linear. Okay, you see here, the derivative can be done. You don't need to compute it with backpropagation or something like this. It's automatic. And because it is so simple, the linear stochastic gradient descent case, that is this rule, this update rule, is one of the most favorable for being analyzed mathematically. And almost all useful convergence results for systems of these kinds are for linear or also simpler than linear function approximation methods. The fact that the cost is quadratic means in particular that the cost is convex, and then there is only one optimum. So here we have for free the guarantee of when the algorithm converges, we have a guarantee of converging to the global optimum, because there is only one optimum. There are not local, not global optimum. Okay, so for instance, the gradient Monte Carlo algorithm converges to the global optimum of the value function, the loss we said in the beginning, that was, for instance, MC converge to arg mean of what we called VA of V under the usual stochastic approximation condition. Okay, so this is, if you're wondering, this is just regression, linear regression. Okay, now what for temporal difference methods? I mean, do they converge? They are same gradient, okay? So they do not converge for the stochastic gradient descent theorem and so on. Well, I told you before that in the linear case, they do converge, okay? Well, this is true, but they do converge to something which is not the global optimum, okay? But, well, this is I mean, not unexpected, at least, because we are not following the full gradient. But they do converge anyway, not to the global optimum. And if you call W temporal difference the solution of linear approximation with this semi-gradient temporal difference, or I don't know if I told you, you can forget this zero, okay? Because temporal difference is part of a family of methods which are called TD lambda, and the temporal difference we are referring to is just consisting in the case of lambda equal to 0. So this is why you can find temporal difference 0. Yes, I could remove from the slides, but sometimes I use the same slides to explain also temporal TD lambda, and so this is why. Also in several papers, they will talk about TD0 instead of temporal difference, so you must get used to it. Okay, going back to the convergence properties. If this is the solution of linear temporal difference, then we have an upper bound for this point. That is, if we compute the loss that we are trying to minimize in the solution given by the temporal difference methods, well, this is close to the minimum we can find with Monte Carlo methods, which is the optimal. I mean, this is the global minima, okay? So this is the best we can find. This is upper bounded by this minimum times this constant. Okay, and this means that the linear temporal difference semi-gradient algorithm is converging near to the global optimum, but not to the global optimum. And how close it is this solution, it is known by this expression. Consider that usually the discount factor is close to 1, and so this is very, very big, this bound. Okay, and similar bounds are known also for the dynamic programming target and for the SARSA target, which is the temporal difference but in the control case. Similar but not the same. Okay, I will not give you the expression. In any case, don't worry about this, because this algorithm is usually working very, very well. This is an empirical statement. There is no theorem proving this. Just empirically, you see that when you use this algorithm on a problem, the solution you find is able to solve the problem in a very good way. That, for instance, for a game can be the fact that in this way, the artificial intelligence you obtain playing that game is able to reach superhuman levels, which means that no humans are able to beat that artificial intelligence in that game. Okay, this would be a sort of empirical evidence that the algorithm is working. Also, if despite the fact that this upper bound constant is very, very big. Okay, and usually you use these methods instead of Monte Carlo methods because of the convergence speed. Okay. Okay, so now that I introduced you the fact that there are different minimum we can compute, different solution we can compute of the problem of finding the minimum of this loss, I would like to discuss the difference in a deeper way, in a more geometrical way. And for this, I will move to this, no, to this, and I will give you 5 minutes rest because starting this. Okay, this is an excerpt from the book, and it is a 3 pages excerpt. We will go through the 2 of the pages. It's very, very, very nice. In fact, I started it with this, you must read this section. But before showing you this, I want to read also a sentence from the book. Maybe I can find the sentence right in the book. Just wait a moment. I need the textbook. one, and I need page 208. Okay, this is the sentence that I want to show you. Critical to this convergence results that I'm discussing now and that I'm discussing later after the post is that the states are updated according to that distribution we were talking about, right? Because we need to follow the environment. If you update the states with other distributions, then bootstrapping methods can completely fail with function approximation. In particular, completely fail means that they can diverge to infinity, not converging at all. So forget the problem of saying if it is converging to the true solution. Okay, you don't have convergence at all. This is a very bad behavior of the bootstrap methods. And okay, and there are examples and possible solution methods in another chapter. Just wanted to point out that it is very important, in particular for bootstrapping methods, to follow the on-policy distribution. That is, to follow the environment and visiting the states in proportions that are the proportions these states appears naturally during episodes. Okay. So I think, of course, if you have questions, you can ask, and otherwise, or in the meanwhile, we can stop a not long pause because I have several other things to say. So I would say just 4 minutes. Let's get back at 3:50.
Okay, perfect.
Okay. So stop video. Okay. So in this section, which is really strongly suggested reading, it's beautiful, there is a geometric description of the value function geometry in the linear approximation case. Geometric description means this picture. Okay, so now I'm going to introduce you the terminology used in this picture. We can read together the caption. Actually, I put some comments, and we will try to understand what does it mean. So first of all, consider or read the highlighted sentences. The space of all possible state value functions are all the functions from the state space to R. Okay, this is a value function. Any value function is this way. Be careful, some of them will be the value function of a policy, some will not, but they are all legit value functions. Okay, yes, this is the meaning of the rest of the sentence. That is this one. It is switching to. Yeah. Okay. This is what I was saying. And what happens is that we are choosing a linear approximation. That means we are choosing in this space of functions, we are choosing a linear subspace given by the parameters, and this linear subspace is of dimension very smaller than the dimension of the of this function space. Okay, the value function are this one. This value function are this kind of function, and of course their cardinality is, for a beautiful chosen notation by mathematicians, the cardinality of the space is r to the power of the dimension of the state space. Okay, so it is a very, very big space. And we can't explore all the space. This is the meaning of the fact that we have too many states. And for this reason, we need to approximate, to choose fewer parameters. Now, imagine that, let's look here. Imagine the case with just 3 states, okay? We just have 3 states here and assume they are too much, so we can't use 3 values to describe this problem, and we can use just 2 parameters, 2 values, okay? So what this means that all value functions are points in a 3-dimensional space. Okay, is this clear? Value functions are, in this case, r to the power of 3, so are just in R3. The value function is a point in R3, and the values given by that function are just the coordinates of this. And the parameters, they are just giving an alternative coordinate system in a 2-dimensional subspace of this R3. Okay, so that any weight vector, which is a vector of 2 dimensions, 2 numbers, will be a point in this 3-dimensional space, but living in a 2-dimensional linear subspace. Okay. And since it is living in this subspace, but it is in the 3-dimensional space, then it is also a value function associated to this parameter W. Okay, and this is what I tried to recap here. In R3, we choose a 2-dimensional subspace. And these 2-dimensional subspace are the value functions which are representable by our approximation methods. Okay. Now, remember we are doing prediction. So consider a single fixed policy. And since we assume that 3 is much, much bigger than 2, we assume that the true value function of this policy is too complex and it is not included in this subspace. It is outside the subspace. And this is expressed by the sentence, cannot be represented exactly as an approximation. Okay. Now, this gives a natural question. If this value function cannot be represented exactly, what is between the representable value function, that is the point in this plane, in the plane of the parameters, of the approximators, which is the point which is closest to this other point? Okay, you are saying, okay, what's the question? You are given a plane, you have a point outside the plane, and you are asking what is the point closer to that plane? Yes, exactly. I will go to the picture now, and then I will go back. So in this picture, the 2-dimensional space is just labeled this way. You can think about the horizontal plane, the XY plane, okay? And you can see the value function here. The true value function is outside this plane, and I'm asking you, what is the closest point of the plane, which is the closest point of the plane to this point in the 3-dimensional space? Okay. What is the answer? Tell me. Well, it should be very easy, actually.
The projection of the point on the plane?
You mean the orthogonal projection with
Yes.
respect to the Euclidean metric, right?
Yes.
Okay,
Yes.
this is the, thank you for asking. Of course, there is more than that. This is a possible answer, okay? In fact, what happens is that this is a subtle question with multiple answers, as you can see here. We need a metric. Clearly, we need a metric to make the projection. And why the Euclidean one should give a better answer than other ones? And actually, there is a reason that I already told you that is giving you something of the opposite. The Euclidean metric is very likely to be not good at all. And maybe we can read here. As discussed in section 9.2, this is the discussion I was giving you at the beginning of the lecture. Some states are more important than others. And what does it mean, are more important than others? Yes, it's sort of our choice, but there is a natural choice that is coming out from the environment, no? Means exactly, as you can see, because they occur more frequently. Because when you look at the episodes, at the trajectories, there are certain states that appears more frequently than others. Or simply for other reason, maybe you're working on a problem, you formalize it as a Markov decision process with several states, but actually this is something you have done because you are interested only in a certain subclass of states. And it was more easy for you to model this problem in a bigger state space, but now you are interested only in certain states. Okay, this can happen in several problems. It's described again in another section with examples. And this means that usually the Euclidean one, that is just one over several possible choices of this importance of states, is usually not the good one. Okay, and we have decided a priori in the beginning of this lecture that we are interested in this kind of this distribution, that is the on-policy distribution, here the terminology, given by the frequency of visits on the states and so on. Okay, in this case, if we choose this distribution, the correct, let's say for the moment correct, the more natural metric to look for is this one. Okay, this is what we called the expected value error. This V, I didn't tell you, V is for value error, and the line over there is for the expectation. And so if we use this expected value error, then things are becoming more natural and more easy. And this is what you are doing in the picture that I'm going to show you right now. Okay, so let's go to this picture. Now, or my writing maybe is making the picture messy than it was in the beginning, but let's have a look at the elements of this picture. This is the true value function, okay? A point in the three-dimensional space. And by assumption, this point is not on the horizontal plane, this one, of the representable value functions. Means the value functions that we can exactly find by our approximation. Okay, our approximation is supposed to approximate things, but sometimes could happen that we are not only approximating, but we are finding exactly the value function we were looking for. In this picture, this would happen only when the value function is in the plane, in the horizontal plane. I repeat that usually you have 100 million parameters and 10 to the power of 200 states. So 100 million parameters means a very small fraction of the total dimensionality of the state space. And this means that it is really never going to happen, with never in a stochastic sense, that the value function you are approximating is exactly representable by your approximation. Okay, so let's start with another notation, which is this one. This is the Bellman operator. What is the Bellman operator? Let me check where it is. Okay. This one. The Bellman operator is the, or maybe it is on the next page also. So let's start from this. Look at this equation. Do you remember what this equation is? Try to tell me. It is written above, actually. Please tell me the name of this equation. It's a very important equation in reinforcement learning.
The Bellman equation.
Thank you. Yes, this is the Bellman equation for value function, meaning that any value function satisfying this Bellman equation is the optimal value function. Okay, you can see this is a fixed point equation. We already talked about this. So it makes sense, given any value function, to plug this value function into this equation in place of this, put any value function, and say that the difference between the two members is a measure of how far is that value function from satisfying the Bellman equation. That is, from being the value function we are looking for. So it makes sense to consider this quantity. You see, this quantity is something that we can call Bellman error. The Bellman error measures how far your approximation, you see, this is not the exact value function, but this is a value function given by the parameter W, is from how far this value function is from satisfying the Bellman equation. So we can call this the error, the Bellman error in the state S. Okay, and this Bellman error is just the expectation of the temporal difference error, because if you rewrite everything here, you understand this is just the sum over the policy and the sum over the model, the distribution model. All of them all together, they give the joint the probability distribution, the underlying probability distribution in your Markov decision process once the policy is fixed. And so you are taking just this with the expected value with respect to this probability. That is exactly this conditional expectation here. And so temporal difference is just sampling this expectation. This is just a small spoiler to let you expect that from this statement that temporal difference will be in some sense related to the minimization of this kind of Bellman error, right? Which is not the expected value error, which is different from the objective VE bar we are using up to now. Okay, if you take the vector of all Bellman errors in this way, and you take their the length of this vector with respect, this is with respect not to the Euclidean norm, but with respect to the norm weighted by the on-policy distribution, well, you obtain a vector, okay? This is the Bellman error on every state, okay? And in picture that I'm going to explain here, this Bellman error, this is here shown by BE, where it is, okay, here, this one. Okay, now, oh, this one, sorry. This one, but this one. Okay, so what is this picture meaning? Remember how the algorithm works. You start from a certain choice of parameters. So you start from a point here. Okay, this point, this choice of parameters means you are choosing a value function, randomly any value function on the plane. Now, if you use a temporal difference method, you are just computing the expectation of the Bellman error vector. But you are representing it, so this is the Bellman operator applied to the value function you started with. Of course, applying the Bellman operator a priori takes you out of the horizontal plane, out of the representable value functions. And when you approximate this value function with your parameters, you are just doing the projection here. So you're going from here again to here. And what you obtain is a new point, which is the projected Bellman value function, the projected value function after applying the Bellman error, okay? And the temporal difference methods, in this sense, is just iterating this process. Okay, and you see from the picture, this iteration of the process is converging. Remember, I told you that semi-gradient temporal difference is converging, and this is exactly the meaning of this picture, and it is converging to something which is this. Is what we call the parameter associated to the temporal difference method. This is by definition the point in the plane where we are converging. And from this picture, you can understand that what we are minimizing is just this distance, the projected Bellman error. That means the difference between what we had before and what we obtain after applying the Bellman operator and projecting. When we reach the temporal difference limit, then this projected Bellman error will be 0. So you can see this is different than minimizing. Not in general will not be this equal to 0. Okay, this is different. And this takes us to the next point, which is number 2 here, which is the solution found by Monte Carlo methods. Monte Carlo methods are instances of stochastic gradient descent, so they approximate in the metric we have chosen, they approximate the true value function. That means they find the closest point with respect to the metric, not the Euclidean one, but with respect to the metric we have chosen in the beginning, because we are sampling states exactly in that proportions. And so no surprise that the Monte Carlo method is giving you exactly the minimum of the expected value error. Okay, and this is number 2. Before going to 3 and 4, I would like ask you if you have questions, if everything is clear. I mean, this picture is really useful. So if it is not clear, find your time reading the first page. It is very, very clear and very easy to understand. Maybe not now that you're tired and so many new notions at once. But if you have questions, this is the right moment to ask them. Okay, no questions. I assume this is a good news. So let's move to point 3. You see there is another point that can be found by algorithms. And I was telling you the Bellman error, what it was. Let's get it again. This was the error. And this was the mean squared Bellman error. Okay, this is what I was referring before. So this is not the Bellman error. The Bellman error is just the difference between these two quantities and this vector qui. This vector here, sorry, mixing Italian with English. This is the Bellman error. That is the BE in the picture. But you can also measure how big is the overall, in overall this vector. And you can measure it in this way, okay? And so you can now ask, you can say it is legit to ask for algorithms that are minimizing this quantity. You see what we are doing? We are finding several legit definitions of what we want to minimize. I mean, it is very natural trying to minimize the Bellman error, because when the Bellman error is 0, the value function is exactly the true value function. So if we minimize in our parameter space the Bellman error, then we can say this is a solution of the problem. And it happens that the temporal difference method is just finding this solution. And this is probably why this solution is usually working very well in solving the problem. Okay. The Monte Carlo methods, on the other way, is finding the minimum of the projection, the projected error from the true value function with respect to the metric we have chosen. Also, that one is a good notion of solution, okay? And also Monte Carlo methods, they works. Now we are saying, okay, we can measure this, the length of this vector, the quadratic length of this vector, and trying to minimize this. And this is called the mean squared Bellman error, denoted by BE with the overline. Well, from here you can find this point, and from the picture you understand that there is a theorem saying that this is different from this, which is different from this, okay? And in the added annotation, I say that I wrote, okay, not here. Okay, I just wrote a comment stating that this quantity is not learnable, and for this reason is useless. I mean, if it is not learnable, you shouldn't try to learn it, of course. What does it mean learnable? You can see in section 11.6, but it's a concept already existing in machine learning. I think here it is used in a slightly different way. Learnable means a quantity that you can that is uniquely given by the distribution of the data. I mean, you can maybe I can just give you the example that is in that section. No, what happens? This and this. I try to explain the concept of learnability in a quick way. We can do this Markov decision process with only one state and with reward 1 and 0 and probability 0, 5, 0, 5. And then we can have a deterministic Markov process doing this, going in this state, going in this state, going in this state, going in this state. And let's say S1, S2, S3. And all of these are deterministic, so they will happen with probability 1, and the reward in this case is 0, 1, 0, 1. Okay, think about these two Markov decision process and imagine you don't know the model. Okay, so we are in the case model free, so you don't have these images. Okay, of course, if you had this image, if you had this, you can compute everything. Everything is learnable from here. You don't have to learn. You're just planning. You're just making computations. So assume you don't know. You want to look at quantities that you can distinguish, that makes you able to distinguish from the two Markov decision process. And if you think of what you are observing from the outside, you are just observing a stream of 0 and 1 with equal probability, right? So whatever you are doing with these two different MDP, MDP1 different from MDP2, whatever you are computing using the distribution of data you are observing cannot distinguish between these two Markov decision process. Okay, I don't know if I was clear. For instance, if you are computing the expected total return, you will always obtain the total return, the expected total return, let's say the value, expected total return, the value of the state that you are observing. You don't know that you are in S1, S2, or S3. You are probably approximating everything with just one single state because you cannot distinguish between them. Then the value of the state is always 1/2. Okay, so also this objective cannot help you. The distribution data cannot help you in distinguish these two Markov decision process. Okay, anyway, it's just to tell you that there is a notion of learnability that means something that you can learn from the distribution data, and it can be shown that this mean squared Bellman error is not learnable. Okay, and I suggest if you are interested, and you should, because it's a beautiful topic, to read the next section in the book, where there is this example and other more elaborated example. Okay, and then there is again a new value, which is this one. This is the minimum of the mean squared expected temporal difference error. Mean square temporal difference error defined here. And if you are scared because this expression looks ugly, don't be scared. This is just the standard temporal difference error. Just have a look. This is the standard temporal difference target. This is the standard error. I'm taking the square of it, and I'm taking the standard expectation with respect to state and action. Okay. And this point 4 can be found by something which is called naive residual gradient algorithm. And also this algorithm is not used because for reasons that are explained in the next example that we are not doing right now. But I'm just telling you a few things that you can use to start a nice geometrical topic from here. Okay. Questions? Checking if there is something that I haven't told you. Okay. So this is what I was saying. Okay, that's all for this excerpt. Okay, questions on this part? Okay, so let's get back to the slides. So remember what we were talking about. We started saying that temporal difference converges, but not to the global optimum. And this global optimum is the one found by the Monte Carlo method. So now we have the picture in mind, and you see that the solution is close to the global optimum, and actually not very close because of this huge bound, but we have found with this geometrical argument that it is solving problems because it is minimizing the projected Bellman error. Okay. And other semi-gradient methods like the dynamic programming method converges to the same point, and the same for Sarsa methods and also multiple step methods, I think. Okay, well, I'm not sure the last sentence actually. Remember, very important, all of this holds with the on-policy distribution, not in general. Okay, if you are interested in the geometry of the space of value functions, I suggest you reading another paper that I have put here, I guess here. Yes, this paper is describing the value function space, and it is proving that the value function space we are talking about is a polytope. That means is a sort of a linear space. Okay, this is very interesting, and well, of course we can't enter into detail, but you can try. I think it would be fun also trying to read this kind of papers that I'm showing you, because I hope you should be able, I think you should really be able to understand them very well. I don't mean the proof and so on that can be deep in some sense, but I mean you can understand the terms, okay? And for instance, here you see stationary policy is a mapping from states to distribution over actions. We denote the space of all policies by probability distribution of a function from the state to probability distribution over actions. And if you see this one, for instance, this, you can guess this is the model. Remember, the probability of getting state S prime from the state S doing the action A. And now you can ask, okay, where is the reward? If the reward is not here, it means that probably in this paper they are considering Markov decision process where when going from a state with a certain action to another state, the reward is unique. There are not cases like the multi-armed bandit, okay, and so on. So I think it is very useful if you try with your time reading this kind of paper, just going through them at least. Okay, so that is a paper on the geometry of the space. Well, here I have a slide on how the features in the linear method can be built, but I will skip this because well, I will skip this, but I will just say one single thing. When we approximate a state in every way, not only in the linear way, we are doing, in some sense, state aggregation. I mean, we are deciding that for a certain value of a certain parameter, then several states are aggregated, are collected all together, and will be not distinguishable from the point of view of the approximator. This is the meaning of approximation. I mean, this means that our Markov decision process is automatically changed into a partially observed Markov decision process. By definition, I'm not able to observe every state. I can just put several of them, aggregate them in subsets from the state space, and each of these subsets will be given by a certain value of parameters. Okay, and this means in particular that I'm losing the Markovianity property. Remember, I told you something like this last week. This is something that you should keep in mind. When doing function approximation, you are losing the Markov property. Maybe your Markov decision process behind all of that is still Markov. But this is just a theoretical property. You can't use it because you are observing just a partial information of the state. Okay, this means that sometimes can be useful to have an agent which is acting not just with a description of the state is looking right now, but maybe preserving some information from the past, maybe using part of the history to preserve Markovianity as much as possible. In this sense, linear approximators are not very powerful, and in this sense, it is much more natural using neural networks with more complex functional structure for the approximator, and maybe neural networks with some kind of memory that are able to memorize in their automatic feature extraction process they can memorize and they can preserve past states, past observations, in this case, I should say. Okay, this was just to say few words to introduce you to the fact that neural networks are usually much better than linear approximator for solving problems, despite the fact that I was saying the linear approximation case is the only one for the moment where we have several theoretical results. Okay, terminology already said, but repeat the Juvan. When the approximation is done by a deep neural network, this is what we call deep reinforcement learning. Okay. Just a remark, I'm talking about neural network, using the word neural network, assuming that you know what they are. If you don't, it's absolutely not a problem. A neural network is just a very powerful approximator. Okay, it's just an approximator, just like just like saying that you have 10 features, and then you are using as an approximator W1 x1 plus W10 x10. This is a linear approximator, right? Where these are the features. Using a neural network means that you are using an approximation of your value function of the form y equal to W1 times something plus W2 times something plus going up to W100 millions. Okay, this is possible with very deep neural networks times something, and all these somethings are function of x1, x2, x3, and something. Oh, sorry, the weight are also not this way. Let's say something also here. Also, the weights are absolutely not put in the linear way, and in every slot I'm picturing in this image, you are putting weights and features in a very non-linear way, okay, in a very intricate way. So it's just a very, very complex functional form of an approximator. It's nothing more, but everything we are saying here, it is the same for linear and not linear. I don't know if I was clear. I was trying to let you not be scared by the word neural networks, but maybe I obtained the opposite. Anyway, trust me, neural networks are just a very, very powerful approximator. It's a different functional form for approximator. Okay, I'm citing this sentence from the book because I think that the sentence is beginning to become outdated. The theory for deep reinforcement learning is now slowly emerging, and however, there is still a lot of room for research. So I think it's very promising. But you can see in 2018, there was this impression that the theory is mostly limited to linear function of tabular ones, which is just a particular case of linear approximation. But already in 2018, actually in 2015, artificial intelligence started having impressive performances using reinforcement learning with approximation given by deep neural networks. Okay, so I think this is sort of quite exciting right now because you can do research from the theoretical point of view, and you can do research from the empirical point of view. You can mix them in whatever amount you like. Now, going to the convergence, next slides are very, very easy. I'm just recapping the convergence properties that I was referring to before. So Up to now, you have seen two families of algorithms. Of course, in the tabular case, both of them converge in the on policy and off policy case. Remember, off policy maybe sounded complicated, but it wasn't. It's just when you collect experience by one policy and you try to learn the optimal policy without using what you're storing for the optimal policy to make experience. I mean, you do experience with another table, okay? You use two different tables and you use one to do experience and the other one to store the values that eventually at the end of the algorithm will represent in some sense the optimal policy. Well, in the tabular case, everything is working. In the linear approximation case, you can see the on-policy methods are working, but the off-policy methods with bootstrapping are not working, and this is worth to be pointed out. This is approximation plus bootstrapping plus off policy. And this is essentially the reason these three things together, deathly triad are called, are essentially the reason why this method is not working. In the nonlinear case, you can see things are much worse. Essentially, just the Monte Carlo method is working because it is unbiased, and the other cases are not working. And there are methods, more advanced methods that recover this kind of loss of convergence, and they are called gradient methods. I will not get into it, but they are very promising methods invented by Sutton in 2011. They are in section 11.7 of the book. And they are the most well understood and widely used stable of policy methods, meaning that they are used in particular, you can see in the off policy case where they recover convergence. Okay, so here we are. Remember that for the moment we were talking about prediction, and now we have the control part. Well, we are now going a little bit faster than before because not because time is ending, but because everything is already done. I mean, everything, I already told you that the hard part is the prediction part. After that, the improvement is made. We now know from the tabular case in which way we can do the improvement. We can do the improvement in the on policy way, that is this one, on policy. Remember, on policy means that you follow an episode with the policy pi, and then you update the values using, you see in the control case, I'm using no more the state value function, but the Q value function. And you can see in the target, this action AT+1 is is choosing. Okay, this is false. Sorry, this is the prediction rule, and this is the prediction improvement rule. You see here, the action, the state, the reward, and so on are obtained following pi, and pi is not changing. So this means that you are just, so this is, trying to erase, but okay. And this is just finding the value of the policy in this case. But if you follow the episode, following the epsilon greedy policy associated to pi, that means that you are taking the table or the approximation, the approximation vector giving the quality value of your actions, and you use that approximation vector to find the epsilon greedy policy that you use to follow the episode, then you obtain this, which is called the TD on policy, temporal difference on policy update rule, which is also known as SARSA 0 for the lambda argument I was telling you before. You can forget this. And this is just the control for the temporal different case. Okay, so nothing more to say. I mean, this slide, we could also avoid it. I mean, it's just the same as in the tabular case. Just take care that we are updating the weight and not the parameter. We are not updating the value of a single state. Okay, just in your head, in your imagination, replace the value of single states, which are cannot no more be singled out one by one. Some of them are collected all together and correspond to a certain parameter. Okay. A remark here, when I have to choose the epsilon greedy action, I need to look at the approximation, and then I need to look at every action I can have in this state. I am in a certain state, right? In order to do epsilon greedy, if I am in the case where epsilon doesn't happen, so I have to choose the greedy action, then I will have to look at every action, possible action, and for choosing the one that my estimates consider better. And in this way, I can choose the greedy action. Well, this is possible only when the actions are not so many, because I need to do this at every step. Okay, so if you have 1 million of action, at every step, with a very high probability, you have to choose between 1 over 1 million of actions, then your algorithm will be really very, very slow and not working. So the action space, in order to use control with function approximation, must be not very big. I would say 1,000 actions are already a little bit too much, but 1,000 action, you can try it. And suitable techniques that can be applied to large action space are a research topic, an ongoing research topic, of course. Okay, the algorithm corresponding to this update rule is just this. We can skip it. It's just the same as in the tabular case. And again, the usual picture that we have in this case is this one. Now we are doing approximate policy evaluation, time step based. Okay, for SARSA, if we are doing with Monte Carlo methods, the time step becomes the episode based. We compute the Q value that is approximating this function. Then we improve and we iterate this picture as usual, this way. Okay. And now we are asking, is it working with function approximation? In the tabular case, we had a theorem stating that eventually we would get closer and closer to the optimal value function. Is this happening right now? In this case, it isn't. Why it is not happening? And this is a question I'm asking to you one of the last questions, I would say. I'm asking you to find the reason, qualitative reason, actually a theorem which is no more true in the approximation case, a theorem that we used very much in the tabular case to say that everything was working, that the control cycle was converging to the optimal function. So what is missing in this theory when we use function approximation? What is missing that we used to have in the tabular case? I'm trying to help you. When I do greedy improvement or epsilon greedy improvement, I'm doing an improvement, right? Somebody pick up the microphone and answer yes, so I can go on.
Yes, absolutely.
Yes.
Oh, perfect. So when I do epsilon greedy improvement, this is an improvement, right? Yes, you said. Is this still true in the approximation case? I mean, I'm still calling it improvement, but in the tabular case, there was a theorem. You remember the name of the theorem?
The policy improvement theorem.
Perfect.
Yeah.
It's a very, very easy name to remember. And what it is stating, the policy improvement theorem, that when I do the epsilon grade improvement, this is actually improving the policy. Do you remember what it means improving the policy? I have pi and I have the new policy pi prime.
The value function is so the new value function at each state is higher than it was before.
Exactly. This way, right? For every state. And with function approximation, do you think this is really happening? I mean, when I change the value of one single parameter, I'm probably changing in the same time, simultaneously, the value of 1 million states. Do you really think that every in these 1 million states is improving its value with the new policy? Absolutely not. We are far away from this. Several of them are decreasing their value. So remember, policy improvement theorem is no more true. There is no such thing with function approximation. It's one of the main reasons why everything is not working in this very easy way that we were used to do in the tabular case. Okay, so it's a very easy reason, but very deep. We have no more the policy improvement theorem. When we are still calling it policy improvement. Okay, I will still say I'm doing policy improvement, epsilon greedy policy improvement, and so on. But we can't say a priori that the policy is improving, and usually it will not. Okay, and this is the mean of the poor convergence results. Okay, so and in fact, what happens is that when you switch to the control case, instead of just staying in the prediction phase, when you use nonlinear algorithms, then you have no convergence at all for this kind of algorithms. Nevertheless, this doesn't mean they don't work, okay? You can still use them for problems and they can work sometimes. It simply means we don't have theoretical background to grasp, to use, to say, oh, this will certainly work. Okay, sometimes you just happen to have this kind of behavior. This kind of behavior is called chattering around in Silver's video. It's something like you go close and closer to the optimal point, to the minimum of your loss that you're looking for, but at a certain point something happens and you go out and you jump off, and then you start going close and close and closer, and then you jump off. And maybe you always remain in a certain neighborhood of that point. And I mean, if this neighborhood is not of a big radius, then probably then the problem is solved anyway. Okay. Anyway, once we introduce function approximation, we can no longer guarantee improvements in any of these algorithms and so on. And this is a very big theoretical problem of this setting, and it is the, let me check, it is the motivation more or less for the next lecture of Friday, that are completely different methods, which are called policy learning methods, that will learn directly the policy, and that has some theoretical, they have a very, very important theorem, sort of a policy improvement theorem in that case. Okay, there is something more that I wanted to tell you, that is the experience replay, and then we are over. Let me check the time. We have 5 minutes. Okay, I will start talking of the experience replay now, but if you have questions about previous sections, please feel free to interrupt me. Okay, experience replay is a way of solving the following problem. The following, I mean, problem. When you do the update, when you use stochastic gradient descent, you visit a state, you evaluate the target, you use this state target for training, and then you discard it, okay? And then you get another state target. You form another training data, and you go on. I mean, if the experience is costly, or maybe you have a finite amount of experience also, not in this case. Let's say just if the experience is costly, it's really a pity not use data, training data again. And in some cases, I mean, if you think about training a neural network for image recognition, you do whatever you can to augment the training set. You modify the images in a slight way, you rotate them, you blur them, you do everything in order to have much more training data from the original training data you used to have. And now we are just using one training data once, so we are not reusing it. So in some cases, it is a good idea to reuse the experience. And this can be done in this way. That is very, I mean, this is put in a formal way, but it is very, very natural. When you form a training sample, that means you have a state, you have an action, and you form the target, which is probably the one step looking forward target, the SARSA target. And instead of using it for training and then discarding it, that means following the on-policy distribution and so on, minimizing the expected value error, as we were saying in the beginning, you just put it in a buffer. And you take the second state, you form the second target, and you do this for all states. Okay, let's say 100 states, let's say 1 million states. You form this buffer, and then you ask, okay, now that I have this buffer, what is the parameter giving me the best fitting function on this training set? Okay, so you forget the on-policy distribution, if you think about it. And well, This means that you're just minimizing this error, and this error, this loss function, this is called the least square. This is the reason of the LS in the name. It clearly depends on the choice of the target. In this case, the target is the SARSA target. Well, in order to minimize this objective, you just do the standard stochastic gradient descent update as usual. And you are just changing, you see, the way how you sample experience. Now you are sampling experience from this finite set D. Of course, when I say this, I mean you are sampling uniformly, and this means that you are minimizing this function, this objective function. You can see here you have no weights. You don't have a distribution probability stating that this training data is more important than this. Okay, all of them are equally important. And so the stochastic gradient descent again minimizes this new objective function. And what I'm saying is that the theorem is this algorithm gives you the argmin of this objective function with, of course, the usual stochastic approximation theory conditions on the learning rate. Okay, why you should do this? Well, there are three reasons. It is more efficient. If the experience is costly, then you can use this way to improve your speed, and also because of the problem we talked about several times. When you're following episodes, the next state will be the next state reward, the next state one step return that you compute will be correlated with the previous one, because the states are correlated with each other. And so putting them in a buffer and taking from that buffer a small amount of them in a stochastic way and keeping the buffer filled in some sense, this improves lowering the correlation, and this helps in convergence speed and properties and so on. And generality. Experience replay is very general. I mean, you can use also other kind of targets. For instance, in the famous AlphaGo family of software, there are several AlphaGo, and the last one is called AlphaGo 0, and this is probably the AlphaGo that one is referring to when one talks about AlphaGo. But we can say there are several algorithms derived from the original AlphaGo algorithm, and they all use a sophisticated sort of experience replay where targets are Monte Carlo targets instead of SARSA targets. And they use these targets to learn estimates of what are called winning probabilities. Okay, this is another story. Okay, and finally.
Sorry.
Yes.
Sorry, maybe I have just a very kind of stupid question. Maybe I lost something. So where is exactly that we are using the experience multiple times? Because we have this buffer, and I mean, we use it once as a whole, right? We have this buffer of, let's say, 1 million different state and rewards, and then we find the W that minimizes the
yes.
list.
Okay, yes, in this slide we are using it just once. When I say, where did I say that we are using it multiple times? Okay.
Oh, maybe just in the very first line, or also.
Yes. Okay, this is a possibility. Yes, I was not clear. This is just a general framework you can use. Maybe I can just, if you want, you can use experience multiple times. I mean, that buffer, you are not forced to discard it, right? You can pass through the experience multiple times. In some sense, choosing stochastically, and you are taking the same training data multiple times. If you are doing several steps of training, right? On
Okay.
average, I mean.
Yeah. Yeah.
And in particular, in AlphaGo, there is this notion of moving window. You take a window of 1 million games, and in this 1 million games, you sample games from this window, and then you move the window with previous games you have, and the overlapping between the two windows is 4/5. And so there is a big overlapping. So when you sample from the new window, there is a high probability that you are sampling multiple times the states. Okay. Anyway, it's a possibility. Yes.
Okay.
You are right that in this slide, from what I'm saying, you're sampling just once. Well, it depends on the number of steps of the stochastic gradient descent you're using, actually. You see, if your buffer contains 100 elements and you take 1,000 steps, on average, you're using the same training data 10 times, each training data 10 times. Do you understand this last?
Yeah, yes, yeah. Okay, makes sense.
Okay, and finally, this is something more of I mean, this is a very, very open problem in reinforcement learning. When you use in the same time these three techniques that you already know, all of them, you use function approximation. Now you know what this means. You use bootstrapping. You know what this means from the first lecture. You use off-policy training. You know this from the second lecture. When you use the three of them in the same time, in the same algorithm, then it's a disaster, probably. Your algorithm is not going to work, probably. I will put in the share folder of papers, a nice paper about this problem. Anyway, why this happens, why this deadly triad of techniques is so deadly, is an open research problem, very, very active. Okay, and okay, here we are. This is a nice sentence, and so let me check the time. Okay. There was still something, but I think we can stop here. I mean, so I had prepared something more very nice, but I think we can stop here. Almost on time.
Okay, thank you, Maurizio.
So are there further questions?
Can we just have the slides, please, by email? Is it possible?
Oh no, I have put them in the share folder this night.
Oh, they are already. Okay, sorry. Thanks. Sorry.
Sorry. Consider, I mean, as soon as they are ready, I put them in the share folder. So probably the night before. I have still to prepare the Friday lecture, so I hope for tomorrow night the slides will be in the share folder. If the slides are not in the share folder the night before, think about me, because it means that I'm working on them.
Can I ask a question?
Okay. Yeah, go on.
All right. I have a question about the dimension of W. So the structure of the neural network. Is that fixed at the beginning, or is it, and how? Or is it relearned at some point?
So you are asking about the dimension, so the number of parameters.
How many layers and that kind of
okay, so,
choice.
I would say your question is related to the problem. When you have a problem, if there is some heuristic, some technique, some way of deciding a priori what is the neural network architecture and dimension that would work better from that problem. Is this the question?
Yeah.
Okay, so the answer is definitely no. With some caveat, of course, experience helps. For instance, if your problem is related to something that is in some sense showing analogies with images, you would be foul not using a convolutional network, because we know from almost 10 years now, from 2012, that convolutional networks are the best way to extract features from images and image-like problems. For instance, in the AlphaGo family, I don't know if do you know the game of Go? How it is, at least how it appears?
Not much, but
Okay,
okay.
the game of Go is played with stones which are black and white. And when you play, it makes sense to look at the shape these black and white stones are forming. Okay, so once you have this remark as a Go player, so you know the shapes are important. I mean, it is not important that the formed shape by the stones are a tree or a house or a known shape. But when you play, a player can recognize shapes which are good and bad in some sense, not very precise sense. Then what DeepMind did when started looking at the Go problem with a neural network and with techniques from reinforcement learning, they said, you know what? Since they talk about shapes, and since we know that convolutional networks are very good in recognizing shapes, then we start trying with a convolutional network. Okay, so this sort of heuristic can help. Regarding the dimension, well, not really. What you do usually is starting with a toy version of your problem and with a toy version of the neural network. In this way, you can make very quick experiments that can help you in deciding whether the approach is correct, meaning the algorithm you're using, Q-learning or Monte Carlo, SARSA, off-policy, on-policy methods, and so on, whether the neural network architecture is correct, and you can then scale up. I mean, if you reduce the dimension of the problem by a factor of 10, and you are using a neural network with 2 layers, or let's say a neural network with 1 million parameter, and this is working well, then for the real problem, which is 10 times bigger, you can, for instance, say, okay, I will use 10 million parameters instead of 1 million, because of course you have also to make some argument giving you that improving the dimension, increasing the dimension of the problem is linearly correlated with improving the dimension of the parameter space. But then the short answer to your question is no. But the long answer is that experience helps, and the much longer answer is that probably there is not a single answer to your question. There is not such an optimal choice. I mean, maybe yes, in a mysterious and magic way, but as soon as you find a solution that works, that solves your problem, that's good.
Okay, thank you.
I have 2 questions.
Go.
The first one is about the Q-learning method. And I wanted to ask you, what if in some environments you have some state in which it is not allowed to perform some actions? For example, you are in a grid world, so you encounter a wall, or you are in the top of the grid, so you can now go up or go into a wall. so empirically, this is solved by putting a mask into the Q table, for example. But what I want to ask you is, if you cannot, if you have a mask on the table, it is still possible to use the. I mean, it's still valid to use the argmax or operator. I mean, in a theoretical way, the policy is still the same. I don't know if I made clear my question.
Yeah, no, I'm not sure it's clear, but we can work making it clear. So you were saying, for instance, I am in a grid world, okay, and I am in a state where there is a wall. Let's say I'm here. So you mean there is a wall here, or there? I don't have possible actions. I don't understand.
Yeah, the top going up is not allowed to you, so you can choose between going left, right, or down.
Okay, I will choose the argmax. Remember, we used the following formalization. When an action is not possible, actually this action is possible, is giving you, in the case of grid world, again, a reward of -1 because you tried something, and this is taking you to the same state. Just like you try to cross the wall and you bounce. Okay.
Okay.
And then we will choose the argmax action. Yes. Why the argmax shouldn't be possible in this case?
No. I mean, I know it is possible, but I was wondering if the policy that you follow, that is using always the maximum argument, is still valid, since you not always have access to all possible actions.
Well, yes. I mean, if you decide you don't have access to all possible actions, you just take the maximum between the remaining actions. And
Okay.
if you have access to all possible actions, but some of them are excluded in this artificial way, saying that they takes you in the same state, then you can still use the max, yes.
Okay. Okay, thank you. And my second question was about the last slide you showed about the three features. Yeah, exactly. And I think that in the paper in which DeepMind achieved the superhuman level on the Atari games, the DeepQ networks, these
Yes.
were all three in it, right?
Perfect. Yes, and that was the first big success in where they succeeded in defeating the deadly triad.
Okay.
And they did this with very advanced technique. One of them is experience replay, that was in some sense eliminating the problem given by correlation. And they were freezing, in some sense, the network that was improving, in some sense, again, eliminating part of the correlation. And yes, but you are right.
Okay.
In that paper, which is from 2015, and you are right that I should definitely put it in the must-read paper. Is one of the paper Nature, of course, from DeepMind. Is the first paper where an artificial intelligence was able to reach superhuman level in several, not every, but several of the Atari games. Space Invaders, to understand, the one Pac-Man, the one we know.
Okay, thank you.
Okay, if there are no further questions,
we can conclude for today, and we will meet again Friday at the usual time.